Hello everybody. So this is a topic that applies not just to binary search trees, but to all kinds of binary trees, but we'll sort of do it in the context of binary search trees. So we're looking at tree traversals. So a tree traversal is just like a process or an algorithm or whatever for like visiting or doing something to all the nodes in a binary tree. It's kind of like the tree equivalent to like a loop over all the nodes, except of course we've already seen that no simple loop is capable of hitting all the nodes in a binary tree here. So this is going to have to be, of course, like some kind of recursive function or some sort of fancier loop or something like that. So we're going to look at four different kinds of tree traversals here. The first three here, these three here, these are going to be recursive. And they'll all actually be pretty similar. And then the fourth one, level order traversal, that one is based on a loop, but it is a loop plus a queue, which keeps track of which nodes we're sort of processing there. So we'll start with the recursive ones and then move on to the loop queue one at the end there. For a binary search tree, the in-order traversal is kind of like the most obvious one. So it gives you the nodes in ascending order, in sort of ascending key value order here. So let's say we have this binary search tree, and we're going to use this tree for like all these traversals here. So like, I don't know, it'll show up in the later ones here, right? So if you just look at the whole tree, right, of course it's, it's easy to list the values in ascending order, but how would you write an algorithm to do it here? So the recursive formulation seems, it's like a lot of recursive things, it's like, that can't possibly work, it's too simple, right? So the idea is just, okay, if the current node is null pointer, then we just don't do anything, right? The tree's empty, there's nothing to do. Otherwise, we're going to recursively explore the left subtree. That's all the things that are less than n, right? Then we're going to do whatever it is we want to do at n, print it or whatever like we're doing there like that. And then we recursively explore everything in the right subtree, which is all the stuff that are greater than n. So an in-order traversal is just this, right? What is that? Like 1, 2, 3, 4, like 5 lines of code? Like that's it. Where I put visit here, that's not an actual function. That's a placeholder for whatever it is you want to do with each of the nodes in the tree. So for example, if you wanted to print the values in the tree in ascending order, you would replace that visit with like cout n arrow key or something like that, right? So like whatever it is you want to do, replace this visit bit with that thing there like that. Visit isn't a real function, that won't compile if you put it into your code there, it's a placeholder. So that's the code, right? But like how does that work, right? Well, if we're looking at a node n, right, where are the values less than n? They're to its left. So that's the stuff that we should do before n. So before we want to do the visit at n, we need to do all the stuff that is less than it, which is in its left subtree there like that. And then, of course, values greater than n are to n's right, not left, like that right there. I obviously copy and pasted that like there. So they should come after. So this here has to come after we visit n there. So then, of course, n itself has to be in between those two things there. Like, again, it seems almost sort of too simple. Like that, how can that possibly work? But it just sort of works out. If you're trying to do it by hand, you can think of this as each node has some like prerequisites before you can visit it, right? So it's like we're sort of checking things off. So for an in-order traversal, the prereqs are we have to have already visited the node's left subtree and the node's left sibling, if it has those things there. So you have to kind of check those things off before we can go to the node itself there like that. So here's an example of an in-order traversal on this tree here. So the first node that we start at is the node with no left subtree, right? There's nothing to the left of this, and no left sibling. There's nothing to the left of it from like a common parent up there like that. So we have to start at the leftmost sort of leaf node in the tree there, which is -4. So we visit -4, and then imagine that like that sort of checks the -4 off, right? I'm going to draw the things that are done that are checked off in gray here, right? So now what is the next node that has either no left sibling or its left sibling is done and it has its entire left subtree done, well, it's 12. So 12 is the next node that we process. I can't do 30 because 30, I haven't done its left subtree down here like that, so I have to do the sort of 12 next there like that. So then we do 12, then we jump down and do 21, then 30, then we do 45. So 45, right, I've finished 45's entire left subtree. 45 does not have a sort of left sibling to process, so 45 is kind of next on my list here like that. Then I go and do a 59, 78, and then finally 88, and then I'm done, like that. So it gives me the nodes in ascending numerical order. Of course, if you wanted descending order, just swap left and right in the code for it there. So there's two variations on the in-order traversal here that are pretty simple tweaks. A pre-order traversal visits the node itself before visiting its descendants. So that just means we take this visit line and put it before the two recursive calls here. So that we visit the node first, then we go left, then we go right there. Again, you can think of this in terms of prerequisites here. So in this case, for a pre-order, a node has its parent, and if it has one, its left sibling as prerequisites. So we can only visit a node after we've checked those off there. We start, of course, at the root, which doesn't have a parent or a left sibling. So here we'll do it again, right? So what node has no parent and no left sibling? It's the root, so that's the first one we do. Now we've checked 45 off, so the next node that we can process, 12 has no left sibling, and we've processed its parent, so 12 goes next. Then 4, again, 4's parents is processed, and 4 has no left sibling, so we do it next there like that. Now, what are we going to do next? We're going to do 30, because 30's parent is done, and 30's left sibling is done there. So we just proceed like that. 30, then 21, then 78, then 59, then 88, and then we're done. Notice how a pre-order traversal is kind of like a top-down kind of thing, right? We hit like the top of the tree, and then we kind of work our way down towards the bottom of the tree, while also working kind of in a left to right order there like that. There's nothing particularly interesting about like the order in which the keys come out here for a pre-order. It's, it doesn't relate to the sort of binary search tree structure there like that. But for other kinds of trees, a pre-order may give you some interesting information. And then finally, the last recursive one we have is a post order, which just puts the visit after the two recursive calls. So we recursively go left and right, and then we visit the node here. So another way, if you want to think of this in terms of prerequisites, the prerequisites for a node are both of its children and its left sibling. Those have to be checked off before we can sort of visit the node here like that. So again, we'll run through a post-order traversal and see what it does here. So again, keep in your mind, we have to check off both our children and our left sibling before we can process ourselves here. So the only node that has no left sibling and no children is the leftmost leaf node here. So that's the first place where we're going to go is our sort of -4 down here. Once we've done that, I can't go to 12 yet because I haven't done both of its children. I can't go to 30 yet because I haven't done both of its children here. So the only other node that has no left sibling and no children that we sort of have here is next going to be 21 like that. So then we do 21, and once 21 is checked off, I can go to 30 because 30's left sibling is done and 30's child is done there like that. Once I do 30, well, now I've checked off both of those children and there's no left sibling over here, so then I can do 21 next there. Now I can't do 45 next until I've done all this stuff over here. So then we do 59, 88, then we can do 78, so both children, left sibling, I do 78, and then once I've done both children and there's no left sibling, I can finally do 45 at the end here. And note that like this order here, the post order, isn't just a reverse of the pre-order here. It's more like a reverse at every level, a recursive reverse kind of thing there like that. The last traversal we're going to look at is a level order traversal. So a level order traversal is different from the other ones. It's going to visit nodes in order of increasing distance from the root. In other words, first it's going to do the things in level 0. So if you remember this from when we talked about binary trees, level 0 is just the root, right? Then it's going to do the stuff at level 1, which is the 2 children of the root. Then it's going to do the stuff in level 2, and so forth, going on down the tree. Level 3, right? So a level order traversal of this would hit the root first, then the root's 2 children, which are 12 and 78. Then the 4 children underneath that, which are -4, 30, 59, and 88. And then finally the last one child down there in level 3 there. So the interesting thing about a level order traversal is that you can't do it recursively, or rather you can't do it with a stack, because of course recursion is based on using a stack. So instead we're going to use a queue to track the nodes that we're visiting here. So remember, the idea of a queue is a queue keeps things fair. So what we want is, while we're sort of exploring a particular level, level K, right, we're discovering children, which are nodes in level K+1. But we want them to wait their turn. We want them to wait until we're done with level K there. So a queue sort of forces the children to wait until after their parents have sort of been finished being processing here. So while we're doing a level order traversal, we're n-queuing the children of nodes while we're visiting it here. This is the sort of like pseudocode for a level order here. I'm not using like any actual particular queue class for this here, but hopefully it's sort of clear enough to see how it works here. Oops, I guess this should be called root. Like that, my bad, sorry. So we create a queue of node pointers, and then we n-queue the root there like that. The way that I've set this up is that null pointer nodes, right, empty nodes, are never in the queue. So we never see sort of like non-existent nodes inside of the queue there like that, right? So as long as the queue is not empty, we're going to pull a node out of the queue. We're going to visit it. And then if it has a left child, we n-queue that. And if it has a right child, we n-queue that. All right, so we're going to trace through the level order traversal on our tree here, showing both the contents of the queue and the order the nodes are visited in here. So again, we start by n-queuing the root. So then we're going to dequeue 45. So 45 comes out, we visit 45, and then we n-queue both of its children. So the contents of the queue are now 12 and 78, there like that. So then again, like the front of the queue is over here. I should have labeled this. The back of the queue is over there. So the next thing to come out is going to be 12. So we pull 12 out. We n-queue 12's children, so 30 and -4, but the queue forces them to wait until after 78 up here has been visited here like this, right? So the stuff on level like K, like that right here, takes priority over the stuff on level K+1. So the next thing to come out is going to be 78. So again, for 78, we're going to n-queue its 2 children, 59 and 88. Those are going to go in there, like that. So now we're just pulling out things on the next level here. So -4 comes out. -4 has no children, so nothing is added to the queue. 30 comes out. 30's child, 21, is added, but it's behind the stuff on this level here, right? So we're going to finish processing this one, which is level 2, before we move on to the next level, which is level 3 there. So 59 comes out, 88 comes out, and then finally 21 comes out there. So that would be the order for a level order traversal. Now, to just do a quick sort of analysis of this stuff here, right? Our goal is to visit or do something at every node in the tree. So of course the runtime has to be O of n. It has to be like, take time proportional to the number of nodes in the tree. What's a little bit more interesting is the memory usage of these algorithms here. So our recursive algorithms, remember that the memory usage of a non-linearly recursive function is the sort of base memory usage of just the function itself, ignoring the recursion. So for these, that's all just O of 1, multiplied by the height of the recursion tree. So for the recursive traversals, the shape of the recursion tree exactly follows the shape of the binary tree, so their heights are the same. So the memory usage is just going to be O of h, or O log of n if the tree is a balanced tree there like that. So we're going to use like log of n memory to do a tree traversal there. For the queue-based one, the level order traversal, the queue contain at most sort of 2 levels of the tree at one time, right? It might have like level K and then some of level K plus 1 there. So the widest 2 levels determine the sort of max memory usage here. The maximum width of any part of a binary tree, depending on its shape, is the number of nodes over 2. So you could have a level order traversal that uses O of n, or like n over 2 sort of memory in the form of the queue there like that. So a level order traversal actually uses more memory theoretically than the recursion based ones there, because it's storing like strips, horizontal strips of the tree rather than sort of vertical paths through the tree there like that. Okay, so those are tree traversals, right? There are sort of methods for visiting all the nodes in a binary tree in some order based on the tree structure there. You got your in-order traversal, which gives you stuff in ascending order, then pre-order and post-order, which just are variations on where do the recursive calls goes there, and then the level order, which is sort of our queue-based things that gives us sort of stuff in stripes from top to bottom there. An interesting thing that I didn't mention in the slide here about level order traversal is if you do a level order traversal and then you insert the values that you get in that order into an empty tree using just a sort of plain Jane binary search tree insert, it will recreate the exact same tree, like the same shape of the tree there like that. So if you want to like, save a tree to disk and then load it back in and have it have the same shape, a level order traversal is the thing that you would sort of want to apply to do that there. Anyway, those are tree traversals there, like another sort of tool for working with binary trees there. That'll do it for now, everybody. Thanks a lot for your time.